When you look up at the night sky, you're witnessing one of the most ancient rhythms of our universe. Stars appear to rise in the east, slowly arc across the vast dome of the heavens, and gently set in the west. This movement has been observed by every human culture throughout history, a constant companion to our existence on this turning planet. What makes this celestial dance so mesmerizing is how all the stars move together, smoothly and predictably. They don't wander independently or drift at random. Instead, they glide across the darkness as one unified tapestry, maintaining their patterns and relationships with one another. The constellation Orion rises with all its stars intact. The Big Dipper wheels overhead with its handle and bowl perfectly preserved. This coordinated movement creates a sense of order and peace in the vastness of space. If you've ever seen long exposure photographs of the night sky, you've glimpsed the true beauty of this motion. These images show star trails as graceful arcs, painting the darkness with luminous curves of light. Each trail is a record of a star's journey across the hours, transformed from a point of light into a sweeping gesture. The photographs reveal what our eyes cannot hold all at once: the elegant geometry of the sky's rotation, captured in glowing ribbons that speak to the passage of time itself. But not all stars follow the same path across our sky. Stars near the North Star, Polaris, behave quite differently. They seem to circle around this fixed point, instead of rising and setting like their celestial companions. If you watch these circumpolar stars throughout the night, you'll see them rotating in patient rings, never dipping below the horizon. They trace complete circles in the northern sky, always visible, always moving, yet always there. This remarkable motion of the stars is not what it first appears to be. The stars themselves are not actually moving across our sky in the way it seems. Instead, Earth rotates west to east, spinning on its axis like a cosmic carousel. As our planet turns in one direction, the sky appears to rotate in the opposite direction, east to west. We are passengers on a rotating world, and the stars provide the steady reference points that reveal our own motion. The rhythm of this rotation is precise and unwavering. One full sweep of the sky takes what astronomers call a sidereal day, which lasts approximately 23 hours and 56 minutes. This is slightly shorter than our standard 24-hour day, measured by the sun. A sidereal day is the time it takes for Earth to rotate once relative to the distant stars, and it's this rotation that creates the grand procession of the heavens we see each night. Every star traces part of a circle each night as Earth spins beneath them. Whether you can see the complete circle depends on where the star is positioned relative to the celestial poles. Some stars, near the poles, complete their circles entirely above the horizon. Others rise and set, showing us only an arc of their circular path before they slip below the edge of the world. Still others, in the opposite hemisphere, remain forever below our horizon, tracing invisible circles we can never see from our particular place on Earth's surface. This motion feels ancient and steady because it is extremely regular. Night after night, year after year, century after century, the stars wheel across the sky with the same reliable rhythm. This constancy provided our ancestors with their first clocks, their first calendars, their first way of measuring the passage of time. The regularity of the stars' motion spoke to something fundamental about the universe, that beneath apparent chaos, there are patterns, rhythms, and laws that govern all things. To help understand and predict this motion, astronomers imagine stars painted on a giant celestial sphere. This is not a physical object, of course, but a useful mental construct. Picture the night sky as if it were the inside of an enormous hollow ball with Earth at the center and all the stars fixed to the inner surface. This imaginary sphere helps us map the positions of stars and describe their movements in mathematical terms. The sphere rotates as Earth spins, or at least that's how it appears from our perspective. In reality, it's we who are turning, but the effect is the same. This celestial sphere completes one full rotation in that sidereal day we mentioned, carrying all the stars with it. By imagining this sphere, ancient and modern astronomers alike can calculate where any star will appear at any time, can predict the rising and setting of celestial objects, and can navigate the complexity of the sky with elegant simplicity. As you drift toward sleep tonight, you can picture this yourself. Imagine the Earth beneath you, turning slowly in the darkness of space. Feel the steady rotation, so smooth we never sense it directly, yet so real that it moves continents and oceans through the cosmos. Above, the stars maintain their vigil, appearing to circle and arc and dance across the heavens, when really it is we who dance, we who turn, we who are in motion through the infinite night. The stars' movement across the sky is both an illusion and a truth. It's an illusion because the stars themselves aren't moving in the ways we perceive. Yet it's a truth because from our perspective, from our place on this spinning world, the heavens truly do wheel overhead. This duality reminds us that perspective matters, that what we see depends on where we stand, and that even our most basic observations of reality are shaped by our particular point of view in the universe. Rest now in the knowledge that this ancient dance continues. While you sleep, the stars will arc across the darkness. They will rise in the east as they always have, sweep across the meridian at their highest point, and set in the west as the horizon claims them once more. And tomorrow night, they will return, perhaps a few minutes earlier than before, maintaining the steady rhythm that has marked the passage of time since long before there were eyes to watch them, and will continue long after we are gone. As we journey deeper into understanding the movement of stars, we come to appreciate the beautiful geometry underlying what we see. Star paths are circles centered on the celestial poles. Every star, without exception, traces a circular path around one of these 2 points in the sky, the north celestial pole or the south celestial pole. These poles are not arbitrary locations, but rather the points where Earth's axis of rotation, if extended infinitely into space, would pierce the celestial sphere. They are the pivots around which the entire sky appears to turn. When we look up and see stars moving in arcs and curves, we're really seeing portions of these circles. Some stars complete their full circle above our horizon. Others rise in the east, trace half a circle through the sky, and set in the west, with the other half of their circular path hidden below the edge of the world. The geometry is perfect, elegant, and unchanging. Each circle is parallel to the celestial equator, and each star maintains its distance from the pole as it moves. It's important to remember that the sky's motion is geometry and perspective, not a solid dome. While ancient peoples often imagined the heavens as a physical sphere rotating around the Earth, we now understand that what we're seeing is the result of our own planet's rotation combined with the vast distances to the stars. There is no actual sphere out there turning. Instead, we're witnessing how the geometry of a rotating planet creates the appearance of a rotating sky. The stars themselves are scattered through three-dimensional space at wildly different distances, yet from our perspective, they all seem equidistant, painted on that imaginary sphere. This distinction between appearance and reality is part of what makes astronomy so fascinating. The dome we perceive is a projection, a two-dimensional representation of a three-dimensional universe, flattened by distance and perspective into something our minds can grasp and navigate. Now, here's where the motion of stars becomes even more intriguing. Star paths look different depending on where you are on Earth. The view from the equator is nothing like the view from Iceland. The perspective from Australia differs dramatically from the perspective in Canada. Your location on our planet fundamentally shapes your window into the cosmos. Your latitude determines how high the celestial pole sits in your sky. Latitude, that measurement of how far north or south you are from the equator, directly translates into the angle of the celestial pole above your horizon. If you're standing at Earth's North Pole at 90 degrees latitude, the North Celestial Pole sits directly overhead at 90 degrees altitude. If you're at the equator at 0 degrees latitude, both celestial poles sit right on the horizon at 0 degrees altitude. And if you're at 40 degrees north latitude, perhaps in New York or Madrid, the North Celestial Pole sits 40 degrees above your northern horizon. This relationship is exact, elegant, and unchanging. Your latitude equals the altitude of your celestial pole. It's one of the fundamental connections between your position on Earth and what you see in the heavens above. Near the equator, stars rise and set almost straight up and down. Imagine standing somewhere close to the Earth's middle, perhaps in Kenya or Ecuador or Singapore. Here, the celestial poles hover right at the northern and southern horizons. Stars rise almost vertically in the east, climb straight upward across the sky, pass nearly overhead, and then descend almost vertically to set in the west. Their paths are perpendicular to the horizon, creating a sense of stars marching straight up from the Earth and plunging straight back down into it. This near vertical motion means that stars don't linger long near the horizon. They rise quickly, spend most of their visible time high in the sky, and set quickly. The twilight is brief near the equator, and the stars waste no time in their ascent and descent. The geometry here is balanced, symmetrical, with equal access to stars from both the northern and southern hemispheres of the celestial sphere. If you could watch the equatorial sky for an entire night, you would witness a remarkable procession. Stars from both hemispheres parade across the zenith, that point directly overhead. In the span of 12 hours, the entire celestial equator passes through the zenith. Stars that were invisible below the southern horizon at dusk climb swiftly upward, pass directly overhead, and descend just as swiftly to set in the north. Meanwhile, stars from the northern celestial hemisphere follow the same pattern, rising in the north, passing through the zenith, and setting in the south. This creates a sense of cosmic abundance at the equator. Unlike observers at higher latitudes who see only a portion of the celestial sphere, equatorial observers have access to the entire sky over the course of a year. Every constellation, every bright star, every celestial treasure eventually becomes visible. The Southern Cross, invisible from Europe and most of North America, rises high in the equatorial sky. Polaris, the North Star that guides travelers in the Northern Hemisphere, sits right on the horizon, marking true north, but never climbing higher. The speed at which stars rise and set at the equator is particularly striking. A star takes only about 2 hours to climb from the horizon to the zenith, that 90-degree journey happening at a steady 15 degrees per hour. This is Earth's rotation rate made visible, 15 degrees of sky passing overhead every hour, or 1 degree every 4 minutes. At the equator, You feel this rotation most directly in the swift rise and fall of the stars. There's also a beautiful symmetry to the equatorial sky. Stars rise due east and set due west, with no deviation north or south. The celestial equator itself runs from the eastern horizon through the zenith to the western horizon, a perfect arc that divides the sky into equal northern and southern halves. Any star positioned on the celestial equator will rise exactly in the east, pass exactly through the zenith, and set exactly in the west, spending exactly 12 hours above the horizon. This geometric perfection makes the equatorial sky particularly elegant to observe and understand. There are no confusing tilted paths, no complicated calculations of rising and setting positions. Everything moves in clean, perpendicular lines. The sky becomes a great wheel turning around you, with you at the center, watching the cosmos rotate past in perfect order. In mid-latitudes, like New York or London or Tokyo, stars follow tilted arcs across the sky. Here, at 40 or 50 degrees latitude, the celestial pole sits partway up the sky, tilting the geometry of stellar motion. Stars still rise in the east and set in the west, but now their paths are slanted. They rise at an angle, sweep across the sky in diagonal arcs, and set at an angle on the opposite horizon. The stars visible from mid-latitudes follow these graceful, tilted trajectories. A star near the celestial equator rises due east, arcs across the southern sky if you're in the northern hemisphere, and sets due west. A star north of the celestial equator follows a shorter, higher arc. A star south of the celestial equator traces a longer, lower path, spending more time near the horizon. This tilted geometry creates the familiar pattern of stellar motion that most people in North America, Europe, and much of Asia experience each night. The tilt of these stellar paths at mid-latitudes creates interesting effects throughout the night. Consider a bright star rising in the east at mid-latitude. It doesn't pop up perpendicular to the horizon as it would at the equator. Instead, it rises at a slant, perhaps 30 or 45 degrees from vertical. This means the star takes longer to clear the horizon, lingering in the murky air near the ground where atmospheric distortion makes it twinkle and shimmer. As this star climbs higher, following its diagonal arc across the sky, it moves both upward and sideways. If you're in the northern hemisphere watching a star south of the celestial equator, the star rises in the southeast, climbs toward the south, reaches its highest point as it crosses the meridian, that imaginary line running from north through the zenith to south, and then descends toward the southwest, setting at an angle that mirrors its rising. The meridian crossing is a significant moment in any star's nightly journey. This is when the star reaches its highest altitude above the horizon, when it's most directly overhead for your location. At this moment, the star is also crossing from the eastern half of the sky to the western half. Astronomers call this transit, and it's the moment when a star is best positioned for observation, highest above the murky horizon air, least distorted by the atmosphere, brightest and clearest. Different stars reach different maximum altitudes when they cross the meridian, depending on their position relative to the celestial equator. A star that lies on the celestial equator will reach an altitude equal to 90 degrees minus your latitude. From New York at about 40 degrees north latitude, a star on the celestial equator crosses the meridian at 50 degrees altitude, roughly halfway up the sky. A star 20 degrees north of the celestial equator crosses the meridian at 70 degrees altitude, nearly overhead. A star 20 degrees south of the celestial equator reaches only 30 degrees altitude at meridian crossing. relatively low in the southern sky. This is why the seasons affect which constellations we see well from mid-latitudes. In summer, the sun is positioned among the northern zodiac constellations, and at night, we see the southern zodiac constellations crossing the meridian. From northern mid-latitudes, these southern constellations like Scorpius and Sagittarius never climb very high. They arc through the southern sky at relatively low altitudes, beautiful but challenged by the thickness of atmosphere we view them through. In winter, the situation reverses. The sun is among the southern zodiac constellations, and at night, we see the northern ones like Gemini and Taurus crossing the meridian at much higher, more favorable altitudes. The tilted paths at mid-latitudes also create unequal seasons of visibility for stars. A star far to the north stays above the horizon for more than 12 hours, tracing a long, high arc across the sky before finally setting. A star far to the south stays above the horizon for less than 12 hours, tracing a short, low arc before quickly setting. This inequality becomes more pronounced the farther you are from the equator. At 40 degrees latitude, a star on the celestial equator is visible for exactly 12 hours. It rises due east, crosses the meridian at 50 degrees altitude, and sets due west. But a star 30 degrees north of the celestial equator is visible for about 16 hours. It rises in the northeast, crosses the meridian at 80 degrees altitude, nearly overhead, and sets in the northwest. Meanwhile, a star 30 degrees south of the celestial equator is visible for only 8 hours. It rises in the southeast, crosses the meridian at just 20 degrees altitude, quite low, and sets in the southwest. This creates a rhythm to the night sky at mid-latitudes. The northern stars are old friends, visible for long hours, climbing high, dominating the sky. The southern stars are brief visitors, skimming along the horizon, offering tantalizing glimpses before departing. The most southerly constellations that can be seen at all from mid-northern latitudes are those barely peeking above the southern horizon, visible only under perfect conditions when the air is clear and the horizon unobstructed. There's also the matter of the seasons and how dramatically they affect the tilted paths. In summer, at northern mid-latitudes, the nights are short, but what night exists is filled with stars following relatively high paths. The celestial equator crosses the meridian at that 50-degree point, and stars near it have excellent visibility. In winter, the nights are long, and those same stars crossing the meridian do so at the same altitude. But now you have many more hours of darkness to watch their full journey from rising to setting. The position where stars rise and set also varies at mid-latitudes in ways that don't occur at the equator. At the equator, every star rises due east and sets due west, but at mid-latitudes, only stars on the celestial equator rise and set at those cardinal points. Stars north of the celestial equator rise somewhere between northeast and due east, depending on how far north they are. Stars south of the celestial equator rise somewhere between southeast and due east. Imagine standing at 40 degrees north latitude and watching the eastern horizon throughout the year. In summer, when the sun is far north on the celestial sphere, you might watch the constellation Leo rising. The bright star Regulus, which lies almost exactly on the celestial equator, rises due east, but the stars in the northern part of Leo rise noticeably north of east. In winter, when Orion is rising, the three belt stars, which lie just south of the celestial equator, rise slightly south of due east. The star Rigel, in Orion's foot and south of the belt, rises even farther south, perhaps 10 or 15 degrees south of due east. This variation in rising and setting positions reflects the three-dimensional geometry of the celestial sphere and our tilted viewing angle. the horizon cuts through the celestial sphere at an angle determined by our latitude, and stars at different celestial latitudes, called declinations, intersect this tilted horizon at different points. For observers at mid-latitudes, there's also a pronounced difference between the visibility of the northern and southern sky. The northern sky, containing the circumpolar stars, is visible all night, every night. These stars never set, circling endlessly around Polaris. The southern sky, in contrast, is transient. Stars rise in the southeast or south, make their brief arc across the southern sky, and set in the southwest or south. The southern sky is a parade of changing constellations, while the northern sky is a constant companion. Near the poles, the sky behaves in an entirely different way. Stars circle the horizon and never rise or set in the traditional sense. Imagine standing near the North Pole, where the North Celestial Pole sits almost directly overhead. Here, stars move in circles parallel to the horizon. They don't rise and descend, but instead wheel endlessly at roughly the same altitude. A star that's 20 degrees above the horizon stays 20 degrees above the horizon all night, all day, all year, simply circling around you. This creates a surreal, almost dreamlike quality to the polar sky. There is no east where stars rise, no west where they set. Instead, the entire visible sky rotates like a great wheel, with you at the hub. Half of the celestial sphere is visible, circling eternally. The other half remains forever below the horizon, invisible from your polar vantage point. Standing at the North Pole itself, at 90 degrees latitude, creates the most extreme version of this phenomenon. Polaris sits directly at the zenith, straight overhead. Every visible star circles the sky at a constant altitude, their paths forming perfect circles parallel to the horizon. A star 10 degrees above the horizon follows a circular path that keeps it exactly 10 degrees above the horizon for its entire circuit. A star 40 degrees above the horizon circles at that precise 40-degree altitude. These circles take a full sidereal day to complete, 23 hours and 56 minutes. Watch a particular star make its circuit, and you'll see it pass through all the compass points. It moves from north to east to south to west and back to north again, never climbing, never falling, just gliding around the sky at constant height. The Big Dipper, instead of rising and setting, simply rotates around Polaris like the hand of a cosmic clock, pointing in different directions at different hours, but always present. The polar sky eliminates the concept of rising and setting entirely. Navigators who've spent time in the high Arctic or Antarctic describe the disorienting quality of a sky where nothing rises and nothing sets, where the same stars circle endlessly, and where the sun itself, during the polar summer, follows a circular path around the sky without ever touching the horizon. For months, the sun spirals in its own circle, creating an endless day. When the sun finally does set, months of night begin, and the stars take over, circling in their patient paths. At the South Pole, the geometry is identical but mirrored. The South Celestial Pole sits at the zenith. Southern circumpolar stars wheel around it at constant altitudes. The Southern Cross circles overhead, along with the brilliant stars of Centaurus and the ethereal glow of the Magellanic Clouds. The entire southern sky presents itself as a rotating dome, unchanging in its components, constantly changing in orientation. As you move away from the pole, even slightly, the geometry begins to shift. At 85 degrees latitude, just a few hundred kilometers from the pole, the celestial pole no longer sits at the zenith, but at 85 degrees altitude. Now, the stars near the pole still circle at nearly constant altitudes, but stars farther from the pole begin to show slight variations in their height above the horizon as they circle. A star that's just barely circumpolar might graze the horizon at its lowest point, nearly dipping below before climbing again. At 80 degrees latitude, this effect becomes more pronounced. Stars circle the pole at 80 degrees altitude, but now there's a noticeable difference between their highest and lowest points in the circuit. Stars that were completely circumpolar at the pole itself might now actually set for a brief time, disappearing below the horizon at the lowest point of their circular path before rising again on the opposite side. By 70 degrees latitude, perhaps in northern Alaska or northern Scandinavia, the polar character of the sky remains strong but is no longer absolute. The celestial pole sits at 70 degrees altitude, high in the sky, but no longer anywhere near the zenith. Stars circle this elevated pole, and many are still circumpolar, but their paths have begun to take on a more elliptical appearance from the observer's perspective. Stars at their highest point in their circle around the pole reach impressive altitudes. The same stars, half a circuit later at their lowest point, come much closer to the horizon. The horizon itself at polar and near-polar latitudes presents an interesting phenomenon. In the continuous daylight of summer, or the continuous darkness of winter, the horizon becomes less a boundary between day and night, and more a simple geometric division between the visible and invisible halves of the celestial sphere. The sun, moon, and planets follow their own circular or near-circular paths, and their relationship to this horizon determines whether they're visible or not. During the polar night, when the sun remains below the horizon for months, the stars circle in perfect darkness. There's no twilight to interfere, no evening or morning transition. When night begins, it's simply continuous darkness that lasts until the sun finally spirals high enough to peak above the horizon months later. This makes the polar night particularly excellent for astronomical observation. The darkness is profound, uninterrupted, and stable. The quality of star movement at polar latitudes also affects how one perceives time. Without the rising and setting of stars to mark the passage of hours, without the familiar progression from eastern horizon to western horizon, time becomes measured differently. The rotation of the entire sky around the pole becomes the clock. Polaris at the zenith doesn't move, but everything else rotates around it, and you can gauge the hour by noting which constellations are in which positions around the pole. For indigenous peoples who've lived in polar regions for thousands of years, this circular motion of the sky is deeply familiar. Their navigation, their timekeeping, their mythology, and stories all reflect this unique celestial geometry. Rather than thinking of stars as rising and setting, they think of stars as circling. Rather than cardinal directions being defined by where the sun rises and sets, they're defined by the circle of the horizon around them. There's something meditative about watching the polar sky, the endless circling of stars, the absence of dramatic risings and settings. The slow rotation of the whole celestial sphere creates a sense of eternal motion, of cycles within cycles, of time marked not by beginnings and endings, but by continuous revolution. The sky becomes a great mandala, rotating around its central point, each star following its ordained path with perfect regularity. These differences in how stars move give rise to one of the most distinctive categories in astronomy: circumpolar stars. Some stars never dip below the horizon, depending on where you're observing from. These are the circumpolar stars, the faithful companions that remain visible throughout the entire night, every night of the year. They never rise because they never set. They simply circle the celestial pole in patient, endless loops. Which stars are circumpolar depends entirely on your latitude. From the North Pole, every visible star is circumpolar. From the equator, no stars are circumpolar because all stars rise and set. From mid-latitudes, there's a band of stars around the celestial pole that never set, while the rest of the sky rises and sets in the familiar pattern. These circumpolar stars endlessly circle the pole in hypnotic patterns. In the northern hemisphere, they revolve around Polaris, the North Star. Familiar constellations like Ursa Major, the Big Dipper, and Cassiopeia are circumpolar from most of the northern United States and all of Canada and Europe. They wheel around the pole throughout the night, sometimes above it, sometimes beside it, sometimes below it, but always visible, always present. The motion of circumpolar stars creates one of the most mesmerizing displays in the night sky. Unlike stars that rise and set, which you can watch for only part of the night, circumpolar stars are available for observation all night long, every night of the year. You can follow a circumpolar constellation through its entire circuit, watching it rotate around the pole like the hand of an enormous clock. The Big Dipper, perhaps the most famous circumpolar constellation for northern observers, demonstrates this beautifully. In early evening during autumn, the Big Dipper hangs low in the northern sky, with its handle pointing downward and to the left. The Dipper appears to be pouring out its contents toward the northern horizon. As the night progresses and Earth continues its rotation, the Big Dipper circles counterclockwise around Polaris. By midnight, it's moved to the left side of Polaris, with the bowl now pointing upward. By pre-dawn hours, the Big Dipper has rotated until it's high above Polaris, with its handle pointing upward and to the right, appearing to pour its contents toward the pole star itself. This rotation continues throughout the day, even though we can't see it in daylight. By the next evening, the Big Dipper has continued its circle and appears in a different position relative to where it was the previous night. Remember that 4-minute daily difference. Over weeks and months, the Big Dipper's position at the same clock time shifts noticeably, tracing out its annual dance around the pole. Cassiopeia, that distinctive W-shaped constellation, performs a similar dance on the opposite side of Polaris. When the Big Dipper is low in the north, Cassiopeia is high. When the Big Dipper circles to one side of the pole, Cassiopeia circles to the other. These two constellations serve as counterweights, forever opposite each other across the pole, both circling endlessly, but never meeting. The circumpolar region itself varies in size depending on your latitude. At the North Pole, the entire visible sky is circumpolar. Everything you can see circles at constant altitude. At the equator, there is no circumpolar region at all. Every star rises and sets. Between these extremes, the size of the circumpolar region exactly equals your latitude. At 40 degrees north latitude, all stars within 40 degrees of the north celestial pole are circumpolar. At 60 degrees north latitude, all stars within 60 degrees of the pole never set. This creates an interesting division of the sky. The circumpolar region is like an exclusive club, a zone of stars that never leave the sky. The boundary of this region is a circle around the pole, and stars just outside this boundary barely skim the horizon at their lowest point, appearing to roll along the northern horizon before climbing back up. Stars just inside the boundary never quite touch the horizon, even at their lowest point, remaining visible all night, every night. From mid-northern latitudes, this circumpolar zone includes not just the Big Dipper and Cassiopeia, but also stars and constellations like Cepheus, Draco the Dragon, and parts of Ursa Minor. The bright star, Capella, in Auriga, is nearly circumpolar from most of the northern United States. It skims very close to the northern horizon at its lowest point, but doesn't quite set for observers at latitudes above about 44 degrees north. The southern hemisphere has its own circumpolar stars rotating around the south celestial pole. The Southern Cross, one of the most iconic constellations in the southern sky, is circumpolar for observers in Australia, Southern Africa, and South America below certain latitudes. The bright stars Alpha and Beta Centauri, the two brightest stars in the constellation Centaurus, circle the South Pole and never set for observers in the deep southern hemisphere. Unlike the North, where Polaris conveniently marks the pole, the South Celestial Pole has no bright star nearby. The pole sits in a relatively dark region of sky, requiring observers to use nearby constellations to find it. The Southern Cross points toward the pole, and by extending a line from the long axis of the cross, you can locate the South Celestial Pole. Circumpolar stars in the south circle this unmarked point, creating the same endless rotation, but without a central star to anchor the view. The fact that different stars are circumpolar at different latitudes creates interesting transitions as you travel north or south. Imagine journeying from the northern United States, perhaps from New York at 40 degrees north, steadily northward. As you travel, the North Celestial Pole appears to rise higher and higher in the sky. Polaris climbs from 40 degrees above the horizon to 50, then 60, then 70 degrees. As the pole rises, more and more stars become circumpolar. Stars that used to set for a few hours each night now circle the horizon at their lowest point without disappearing. The circumpolar region expands like a growing cap over the northern sky. By the time you reach the Arctic Circle at about 66 degrees north latitude, the circumpolar region has expanded dramatically. Stars that barely rose above the horizon from New York now trace large circles high in the sky. The entire character of the night sky has transformed. Travel far enough north, and eventually you reach latitudes where bright, familiar stars that always used to set become circumpolar. From northern Alaska or northern Scandinavia, even stars like Vega, brilliant in the summer sky, become circumpolar. Vega never sets, instead circling the pole at lower altitudes during its minimum height, then climbing high during its maximum. The opposite happens as you travel south from northern latitudes toward the equator. The North Celestial Pole sinks lower and lower toward the northern horizon. Polaris descends from its elevated position. The circumpolar region shrinks. Stars that never set begin to graze the horizon, then dip below it for brief periods, then set for longer and longer intervals. By the time you reach 30 degrees north latitude, perhaps in Morocco or Houston, the circumpolar region has shrunk considerably. Only stars very close to the pole remain circumpolar. The Big Dipper, which was fully circumpolar farther north, now has its lower stars actually setting for a short time each night. Continue south to the equator, and the last vestiges of circumpolar stars disappear. At 0 degrees latitude, the celestial poles sit exactly on the horizon. North Pole due north, South Pole due south. Every star in the sky rises and sets. There are no circumpolar stars, no never-setting companions. The entire celestial sphere rotates past the observer, half of it visible above the horizon at any given time, the other half hidden below. But cross the equator and continue south, and a new circumpolar region begins to grow around the South Celestial Pole. Stars that were always hidden below the northern horizon now appear, circling the South Pole. The Southern Cross, invisible from northern latitudes, becomes circumpolar. The Magellanic Clouds, those companion galaxies to our Milky Way, circle the South Pole endlessly. An entirely new set of never-setting stars takes over the role that the Big Dipper and Cassiopeia played in the north. This transformation of the circumpolar region as you travel in latitude is one of the most tangible demonstrations of Earth's spherical shape and your changing perspective on it. The stars haven't moved. They maintain their positions in space. But your viewing angle has changed, and with it, your entire relationship to the sky. Stars that were faithful companions, never setting, become transient visitors. Hidden stars emerge. The geometry of the celestial sphere reveals itself through your motion across Earth's curved surface. The sky can be divided into 3 regions based on your latitude. Other stars rise and set, while some are never visible at all. Stars close enough to your celestial pole never set. These are the circumpolar stars we've discussed. Stars in the middle range rise in the east, arc across your sky, and set in the west. These are the rising and setting stars that make up most of what we see on any given night. And stars close to the opposite celestial pole never rise above your horizon. These are the never visible stars, the hidden half of the sky you can never see from your particular latitude. From New York, you can never see the Southern Cross or the Magellanic Clouds. They belong to the southern sky, circling the south celestial pole, which sits permanently below your southern horizon. From Sydney, you can never see Polaris or much of Ursa Major. They circle the north celestial pole, hidden below the northern horizon from that southern vantage point. Traveling north or south changes which stars belong to each group. This is one of the most magical experiences in astronomy. As you journey across the Earth's surface, the sky transforms. Travel south from Canada toward the equator, and you'll see the north celestial pole sink lower and lower toward the northern horizon. Stars that were circumpolar begin to graze the horizon, then start setting. Meanwhile, new stars that were never visible begin to peak above the southern horizon. Stars you've never seen before rising from the south. Cross the equator, and the transformation is complete. The south celestial pole, which was always hidden, now sits above the southern horizon. Entirely new circumpolar stars wheel around this new pivot point. The southern sky opens up with unfamiliar constellations, brilliant star clouds of the Milky Way, and celestial objects that were previously hidden below the curve of the Earth. This shifting view reminds us that we live on a sphere, that our perspective is local and limited, and that there are skies beyond our sky, visible only to those who stand on different parts of our shared world. The stars haven't moved. We have. And in our movement, the geometry of the cosmos reveals itself in new and wondrous ways. As you settle into rest, imagine this grand geometry. Picture the circular paths of stars around the poles, the way your latitude determines what you can see, the tilted arcs or vertical rises or endless circles that stars trace, depending on where you stand. And know that somewhere, right now, someone else is watching the same stars from a different angle, seeing them move in a different way, yet all of us connected by the same rotating Earth, the same celestial sphere, the same ancient dance of perspective and motion that has fascinated humanity since the first person looked up and wondered. Among all the movements we observe in the night sky, perhaps none are more familiar than the constellations. These patterns that ancient peoples saw in the stars continue to guide our gaze today. Constellations move as rigid patterns across the heavens. Unlike clouds that shift and change shape, or planets that wander independently through the sky, the constellations maintain their forms perfectly as they journey from east to west. When Orion rises in the east, his belt, his shoulders, and his sword rise together, maintaining the same arrangement they've held for thousands of years. The Big Dipper wheels around the North Pole with its handle and bowl intact. Scorpius crawls along the southern horizon with its curved tail following its bright heart. These patterns move, but they move as unified wholes, as if they were indeed painted on that celestial sphere we've imagined. The shapes rotate and flip but do not stretch or distort. As a constellation rises, it may appear tilted compared to when it's high overhead. As it sets, it may seem to roll toward the horizon. From different latitudes on Earth, a constellation might appear upside down or rotated to an unfamiliar angle, yet the internal geometry of the pattern never changes. The distances and angles between the stars within a constellation remain constant. The pointer stars of the Big Dipper always point toward Polaris with the same relationship. The 3 stars of Orion's belt always march in their perfect diagonal line. This constancy is remarkable when you consider that stars are actually individual suns scattered through space at vastly different distances from us. The stars in any given constellation are rarely related to each other at all. They simply happen to lie along similar lines of sight from our perspective. Yet despite their true separation in 3-dimensional space, they appear locked together in 2-dimensional patterns on our sky. The distances between stars appear fixed over a lifetime, and indeed over many lifetimes. A person born today will see the same constellation patterns that their great-great-great-grandparents saw. The stars do have their own individual motions through space, what astronomers call proper motion. But these movements are so slow relative to the vast distances involved that centuries pass before any noticeable change occurs in constellation shapes. Ancient astronomers called them fixed stars for this reason. Unlike the wandering stars, the planets, whose name means wanderer in Greek, the regular stars seemed permanently fixed in their patterns. They rotated with the celestial sphere, but they didn't move relative to each other. This fixedness made them reliable, dependable, perfect for navigation, for timekeeping, for marking the passage of seasons. The fixed stars were the stable background against which all other celestial motions could be measured. And yet, there is another motion to discover, one that happens so gradually you might not notice it from night to night, but which becomes unmistakable over weeks and months. This is the slow drift of the seasons, written in the stars. Stars rise about 4 minutes earlier each night. This subtle shift is the consequence of that sidereal day we discussed earlier. Earth takes about 23 hours and 56 minutes to rotate once relative to the stars, but our clocks are based on the solar day, the time it takes for the sun to return to the same position in the sky, which is exactly 24 hours. This 4-minute difference between a sidereal day and a solar day accumulates night after night. If a particular star rises at exactly 9 o'clock tonight, tomorrow night it will rise at about 8:56. The night after that, 8:52. 4 minutes earlier each night, 2 hours earlier each month, completely around the clock over the course of a year. This steady drift means that if you observe at the same clock time each night, the constellations appear to shift westward across the sky. This 4-minute daily shift has profound consequences for how we experience the night sky over time. It means that the sky you see at 10 o'clock tonight is slightly different from the sky you saw at 10 o'clock last night, which was different from the sky at 10 o'clock the night before. Each night, Earth has progressed a little farther in its orbit around the Sun, and the stellar background has shifted westward by about 1 degree, roughly twice the width of the full moon. Over a week, this adds up to about 30 minutes of shift, or roughly 15 degrees of sky, about the width of your outstretched hand at arm's length. Over a month, it's 2 hours of shift, or 30 degrees. Over 3 months, 6 hours, or 90 degrees, a quarter of the complete circle. Over 6 months, 12 hours, or 180 degrees, the sky has completely reversed. Over a full year, the cycle completes, and the sky returns to its starting configuration. This creates a wonderful predictability to the night sky. If you note the position of a constellation tonight at a particular time, you can predict exactly where it will be tomorrow night, next week, next month, next year. Orion rising at 8 p.m. tonight will be rising at about 7 p.m. a month from now, rising at sunset 3 months from now, and setting at sunset 6 months from now, invisible in the daytime sky. Imagine going outside at 10 o'clock every evening throughout the year and noting which constellations are visible. In early January, you might see Orion high in the southern sky, the Pleiades star cluster overhead, and Gemini rising in the east. These are the characteristic constellations of winter evenings. The brightest star in the sky, Sirius, blazes in the south. Taurus the bull with his bright red eye, Aldebaran, dominates the southwest. A month later, at the same 10 o'clock hour, the scene has shifted westward. Orion has moved noticeably toward the southwest. The Pleiades, which were overhead, are now to the west. Gemini, which was rising in the east, is now well up in the southeastern sky. New constellations have appeared in the east. Leo the lion is climbing above the eastern horizon, announcing the approach of spring. By early March, 2 months later still, the transformation continues. Orion is setting in the west as 10 o'clock arrives. The winter constellations are departing. Leo is now high in the southeast, the distinctive backward question mark of stars forming his head and mane clearly visible. Virgo is rising in the east, and the bright star Arcturus in Bootes is climbing in the northeast. The spring sky is taking over. By early April, Orion has vanished from the evening sky entirely, setting before darkness falls. The winter constellations have completed their season. Leo dominates the southern sky. The Big Dipper, circumpolar though it is, has rotated to a position high overhead, its handle pointing downward and creating the famous saying, "Arc to Arcturus." Follow the arc of the Dipper's handle, and you'll reach the bright orange star Arcturus in Bootes. Come May, and the spring constellations are at their prime. Leo crosses the meridian at 10 p.m., reaching his highest point. Virgo is well placed in the south. Arcturus blazes high in the east. The stars of summer are beginning to appear. Vega, the brightest star of summer, peaks above the northeastern horizon. The sky is transitioning again. By June, summer is announcing itself. Leo is moving west. Virgo crosses the meridian. Arcturus is high overhead. Vega has climbed well up in the east, and other summer stars are appearing. Deneb in Cygnus the swan, Altair in Aquila the eagle. The summer triangle is forming, though it won't reach its prominent position until later in the season. July brings the full summer sky. The spring constellations are setting in the west. The summer constellations dominate. At 10 p.m., the summer triangle, Vega, Deneb, and Altair, is rising in the east and northeast, climbing toward its eventual position high overhead. The Milky Way, that glowing band of billions of distant stars, arches across the sky from north to south. most prominent in the darkness of a summer night far from city lights. August sees the summer triangle high overhead at 10 p.m. Vega shines nearly at the zenith from mid-northern latitudes. The Milky Way is spectacular, running through Cygnus and down through Sagittarius in the south, where the center of our galaxy lies. The summer constellations are at their prime, and the nights are warm and inviting for stargazing. But by September, change is again underway. At 10 p.m., the summer triangle has moved to the southwest. The autumn constellations are rising in the east. Pegasus, the great square of autumn, climbs above the eastern horizon. Andromeda, chained princess of mythology, rises beside Pegasus. Fomalhaut, often called the autumn star, shines in solitary splendor low in the south. October brings the full autumn sky. The summer triangle is setting in the west. Pegasus dominates overhead. Andromeda stretches to the northeast. The autumn sky is often described as more somber than summer, with fewer bright stars and larger expanses of darkness between the constellations. But it has its own beauty, a quieter majesty. By November, Pegasus crosses the meridian at 10 p.m. Andromeda is well placed high in the sky, and in the east, the winter constellations are returning. Taurus is rising, the Pleiades climbing above the horizon. Orion himself is beginning to appear in the late evening, rising in the east around midnight but visible before bedtime in the eastern sky. December completes the cycle. Orion is back in the evening sky, rising earlier and earlier. By late December, Orion is well up in the east by 10 p.m. Taurus is high overhead. The Pleiades blaze in the south. The brightest stars of winter, Sirius, Capella, Aldebaran, Rigel, Betelgeuse, create a dazzling display. The year has come full circle, and the sky has returned to its winter configuration. This annual progression is one of the most reliable rhythms in nature. For thousands of years, humans have used these seasonal skies as calendars, marking the passage of time by which constellations appear in the evening sky. Before clocks, before written calendars, the stars were the primary way to track the year's progress. Imagine going outside at 10 o'clock every evening. In early September, you might see the bright star Vega high overhead. A few weeks later, at the same 10 o'clock hour, Vega has moved noticeably to the west. By late October, it's setting in the west as darkness falls. By December, Vega sets before 10 o'clock even arrives. The star hasn't changed its behavior. Earth's orbit around the sun has shifted our perspective, and our clock time observations reveal this shift as a westward drift of the entire stellar sphere. Over months, whole sets of constellations disappear and return. This is perhaps most noticeable with the bright, prominent constellation patterns that mark the seasons. Orion, that magnificent winter constellation, dominates the sky on January evenings. By April, Orion is setting in the west as darkness falls. By June, Orion is lost in the twilight, setting with the sun, completely invisible. The hunter has vanished from our sky. But Orion hasn't gone forever. Through the summer months, while we cannot see it, Orion is in the daytime sky, lost in the sun's glare. By late autumn, Orion begins rising in the early morning darkness before dawn, announcing its return. And by the next January, Orion is back in the evening sky, exactly where it was a year before, as if the constellation had journeyed away and returned home. This creates seasonal skies, winter, summer, spring, and autumn, each with their characteristic constellations. Winter brings Orion, Taurus, Gemini, and the brilliant star Sirius. Spring ushers in Leo, Virgo, and the arc of the Big Dipper's handle. Summer evenings showcase Cygnus, Lyra, and Aquila, forming the summer triangle high overhead. Autumn returns Pegasus, Andromeda, and the scattered stars of the fall season. Each group of constellations marks its time, disappears, and returns in an endless cycle tied to Earth's journey around the sun. Our ancestors used these seasonal skies as calendars. The first appearance of certain stars at dawn, what astronomers call heliacal rising, marked important times of the year. In ancient Egypt, the heliacal rising of Sirius announced the annual flooding of the Nile. In Greece, the rising of the Pleiades signaled the time for harvest. These stellar calendars were more reliable than the moon, more visible than subtle changes in the sun's position, and they connected human activity to the grand cycles of the cosmos. At the heart of this seasonal drift is the sun's own apparent motion through the stars. The sun moves along the ecliptic about 1 degree per day. The ecliptic is the path the sun appears to trace against the background stars over the course of a year. It's actually the projection of Earth's orbit onto the celestial sphere. But from our perspective, it appears as if the sun is journeying eastward through the constellations, while everything else moves westward. 1 degree per day is a slow and steady pace. The sun travels through its entire 360-degree circuit in approximately 365 days, 1 year. Each day, the sun appears in a slightly different position among the stars, moving through one zodiac constellation after another. This motion is hard to observe directly because we can't see the stars near the sun during daylight, but we can infer the sun's position by noting which constellations are opposite the sun at midnight, high in the darkest sky. This 1 degree per day motion is the fundamental cause of that 4-minute daily shift we've been discussing. As Earth orbits the sun, we're constantly changing our viewing angle on the stellar background. Each day, Earth moves about 1/3600th of the way around its orbit. This changes our perspective by 1 degree, which corresponds to 4 minutes of rotation time. It's as if Earth needs to rotate an extra degree each day to bring the sun back to the same position in the sky, and that extra degree takes 4 extra minutes beyond the sidereal day. Think of it this way. If Earth only rotated but didn't orbit, the stars would rise at the same time every night according to our clocks. But because Earth is also orbiting, constantly shifting position in space, the stars appear to drift westward in clock time. That drift is the visible consequence of our orbital motion. The ecliptic itself is a fascinating feature of the sky. It's tilted 23.5 degrees relative to the celestial equator, that projection of Earth's equator onto the sky. This tilt reflects the fact that Earth's axis is tilted 23.5 degrees relative to its orbital plane. Because of this tilt, the sun doesn't follow the celestial equator. Instead, it wanders north and south of it throughout the year, tracing out the ecliptic. In late March, around the vernal equinox, the sun crosses the celestial equator going northward. It's moving from the southern half of the sky into the northern half. Over the next 3 months, the sun continues northward along the ecliptic, reaching its maximum northern distance from the celestial equator, 23.5 degrees north, around the summer solstice in late June. During this time, the sun rises in the northeast, climbs high in the sky at noon from northern latitudes, and sets in the northwest. The days are long, the nights short. After the summer solstice, the sun begins its return journey southward along the ecliptic. Through July, August, and September, the sun moves back toward the celestial equator, which it crosses going southward around the autumnal equinox in late September. The days and nights are again equal in length as they were at the vernal equinox. The sun continues southward through October, November, and into December, reaching its maximum southern distance from the celestial equator, 23.5 degrees south, around the winter solstice in late December. From northern latitudes, the sun rises in the southeast, stays low in the southern sky at noon, and sets in the southwest. The days are short, the nights long. After the winter solstice, the sun begins moving northward again along the ecliptic, and the cycle repeats. This annual journey of the sun along the ecliptic creates our seasons. When the sun is far north on the ecliptic, it's summer in the northern hemisphere. The sun is high in the sky, providing more direct sunlight, and the days are long. When the sun is far south on the ecliptic, it's winter in the northern hemisphere. The sun is low, providing less direct sunlight, and the days are short. The ecliptic passes through 13 constellations, though traditionally, only 12 zodiac constellations are recognized. Starting from the vernal equinox point and moving eastward along the ecliptic, the sun passes through Pisces, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius, Ophiuchus. Not traditionally considered a zodiac constellation, Sagittarius, Capricornus, Aquarius, and back to Pisces. The sun spends different amounts of time in different constellations because the constellations are different sizes and the ecliptic doesn't pass through them uniformly. The sun spends only about a week in Scorpius, but nearly a month in Virgo. These are the modern astronomical facts, which differ from traditional astrological divisions that divide the ecliptic into 12 equal 30-degree segments, each assigned to a zodiac sign regardless of the actual size of the constellation. As the sun moves along the ecliptic, it's not moving in isolation. Earth is moving, carrying us along our orbital path. We're traveling through space at about 30 kilometers per second, or roughly 108,000 kilometers per hour. That's extraordinarily fast, yet we feel none of it. The motion is smooth, constant, and there's no resistance in the vacuum of space to create any sensation of speed. This orbital motion has another subtle effect on stellar positions beyond the 4-minute daily shift. Because we're viewing the stars from different positions in our orbit, nearby stars show a tiny parallax shift over the course of the year. We discussed this earlier, how nearby stars appear to wobble slightly against the background of distant stars as Earth orbits the sun. This parallax is incredibly small, less than 1 arcsecond even for the closest stars, but it's real and measurable. The combination of Earth's rotation and Earth's orbit creates a complex dance of apparent stellar motions. The rotation causes the daily rising and setting, the nightly march of stars from east to west. The orbit causes the seasonal shift, the annual progression of different constellations through the evening sky, and the subtle parallax wobble of nearby stars. Together, these motions create the dynamic, ever-changing yet ultimately predictable night sky we observe. Throughout history, careful observers noticed that the sun's path through the stars, the ecliptic, was also followed by other celestial wanderers. The moon, in its monthly orbit around Earth, stays close to the ecliptic, weaving slightly above and below it, but never straying far. The planets, too, travel along or very near the ecliptic. This is not coincidence, but consequence of how the solar system formed. About 4.5 billion years ago, our solar system coalesced from a rotating disk of gas and dust surrounding the young sun. This disk was flat, like a cosmic pizza, with most of the material concentrated in a single plane. As planets formed from this disk material, they naturally inherited orbits in that same plane. When we look at the solar system from afar, we see all the planets orbiting in nearly the same flat plane, like grooves on a record, When we project this orbital plane onto the sky, it becomes the ecliptic. So when you see Venus shining brilliantly in the evening sky, it's somewhere along the ecliptic. When Mars appears as a red star among the constellations, it's traveling through or near the zodiac. When Jupiter and Saturn, those giant worlds, have one of their rare conjunctions appearing close together in the sky, they meet along the ecliptic. The moon's path is particularly interesting. The moon orbits Earth once every 27 1/3 days, relative to the stars. But because Earth is also orbiting the sun, the cycle of lunar phases, new moon to full moon and back to new moon, takes about 29.5 days. During this time, the moon traces a path through the zodiac constellations, moving eastward against the stellar background at about 13 degrees per day. This means the moon moves its own diameter, about half a degree, in roughly 1 hour. If you watch the moon carefully over an hour or two against a backdrop of stars, you can actually see it moving, shifting position relative to the background stars. The moon's motion is fast enough to be perceptible over short time scales, unlike the slow drift of the sun or the imperceptible motions of the planets over a single night. The moon's path wobbles slightly above and below the ecliptic because the moon's orbital plane is tilted about 5 degrees relative to Earth's orbital plane. This means the moon can appear up to 5 degrees north or south of the ecliptic as it travels through the sky. Sometimes the moon passes through the northern zodiac constellations, appearing high in the night sky from northern latitudes. Sometimes it passes through the southern zodiac constellations, appearing lower in the sky. The planets each have their own orbital periods and their own relationships to the ecliptic. Mercury, closest to the Sun, orbits every 88 days and stays close to the Sun in the sky, visible only briefly after sunset or before sunrise. Venus, the second planet, orbits every 225 days and also stays relatively close to the Sun, appearing either as the evening star in the western sky after sunset or the morning star in the eastern sky before sunrise. Mars, the red planet, orbits every 687 days, about 2 Earth years. This means Mars takes roughly 2 years to make one complete journey through the zodiac. Mars is often visible in the evening sky, moving slowly eastward through the constellations over weeks and months, though occasionally it exhibits retrograde motion, appearing to move westward for a time before resuming its eastward journey. Jupiter, that giant world, orbits every 12 years. This means Jupiter spends about 1 year in each zodiac constellation, slowly making its way around the sky. If you note Jupiter's position among the stars this year, it will be in a different zodiac constellation next year, and 12 years from now it will return to approximately the same position. Saturn, even farther out, orbits every 29.5 years. Saturn creeps very slowly through the zodiac, spending about 2.5 years in each constellation. Ancient observers watching Saturn throughout their lives would see it make only 2 or 3 complete circuits of the sky. All these planetary motions occur along or near the ecliptic, that special path that ties together the sun's apparent motion, the moon's orbit, and the planet's wanderings. The zodiac constellations serve as the backdrop for this cosmic dance, the stage upon which the major players of the solar system perform their gravitationally choreographed movements. The zodiac constellations lie along this path, the ecliptic. These 12 traditional constellations, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius, Sagittarius, Capricornus, Aquarius, and Pisces, form a band around the sky through which the sun, moon, and planets all travel. The zodiac is the highway of the solar system, the plane in which the major objects orbit, projected onto the dome of stars. When we say the sun is in a particular zodiac constellation, we mean that if we could see the stars during the day, the sun would appear to be positioned in front of that constellation's pattern. A person born when the sun is in Taurus would have been born when Taurus was rising with the sun, invisible in the daylight, while Scorpius, opposite in the sky, was setting with the night. 6 months later, when the sun has moved to Scorpius, Taurus rises in the east as the sun sets in the west, and Taurus becomes an evening constellation. This stately procession of the sun through the zodiac creates the rhythm of the year. It explains why different constellations dominate different seasons. It reveals the geometric relationship between Earth's orbit and the patterns we see in the sky. The sun's slow eastward drift against the stars, combined with Earth's daily westward rotation of the sky, weaves together to create the complex dance of appearances and disappearances, risings and settings, seasonal skies and returning patterns that have structured human timekeeping since the beginning of civilization. As you rest tonight, you might reflect on this layered motion, the daily rotation that carries the stars from east to west, the seasonal drift that shifts the constellations westward each night, the sun's patient journey through the zodiac, marking the year. All of these motions are really our own motions seen from the inside, living on a planet that spins and orbits through space. The fixed stars are our reference frame, the stable background that reveals our own graceful movement through the cosmos. The constellations will continue their rigid dance, unchanged in form, shifting in position with the hours and the seasons. They will disappear into the sun's glare and emerge again in the darkness. They will mark time, mark seasons, and mark our place in the turning year. And though we cannot feel the Earth's motion beneath our feet, the stars write that motion across the sky in patterns anyone can learn to read, patient and eternal, night after night, season after season, year after year. We've explored how the sun moves along the ecliptic, progressing through the zodiac constellations at about 1 degree per day. But this motion creates an interesting paradox. When the sun is in a constellation, that constellation is hidden in daylight. The sun's brilliance washes out the stars around it, making them invisible against the bright blue sky. If the sun is positioned in front of Gemini, then Gemini rises with the sun, crosses the sky with the sun, and sets with the sun, completely lost in the solar glare. This means that the constellation associated with your birth, your sun sign in astrological terms, is actually the one constellation you cannot see on your birthday. It's hidden behind or near the sun, drowned in daylight. The sky plays this quiet trick on us, concealing the very pattern that marks our birth time in the calendar. But the cosmos offers compensation for this loss. 6 months later, that constellation dominates the night sky. When Earth has traveled halfway around its orbit, we find ourselves on the opposite side of the sun. Now that constellation, which was lost in daylight, rises as the sun sets. It climbs high overhead at midnight, positioned directly opposite the sun in the sky. It dominates the darkness for weeks, visible all night long before gradually shifting westward as Earth continues its journey. If you were born when the sun was in Gemini, then 6 months later, in late November and December, Gemini rides high in the night sky. If your birth constellation was Sagittarius, then in late May and June, Sagittarius stretches across the midnight darkness. This celestial symmetry means that every constellation has its time hidden and its time revealed, its season of invisibility and its season of prominence. The sun is not alone in its journey along the ecliptic. Planets and the moon also wander this same band. The zodiac is not just the sun's path, but the highway for all the major bodies of the solar system. The moon, in its monthly orbit around Earth, traces a path that stays close to the ecliptic, weaving slightly above and below it, but never straying far. The planets, Mercury, Venus, Mars, Jupiter, and Saturn, visible to the naked eye, all travel within this same zodiacal band. This is not coincidence, but consequence. The solar system formed from a disk of material orbiting the young sun. That disk was essentially flat, and the planets that coalesced from it orbit in nearly the same plane. When we project that plane onto the sky, it becomes the ecliptic. So when you see Venus shining brilliantly in the evening twilight, it's somewhere along the zodiac. When Mars appears as a red star among the constellations, it's traveling through the zodiacal band. When Jupiter and Saturn have their rare conjunctions, appearing close together in the sky, they meet along this ancient highway that the sun travels. The wandering of these planets against the fixed stars fascinated ancient astronomers and gave us the name planet itself, from the Greek word for wanderer. While the stars maintained their patterns and rotated rigidly together, the planets had minds of their own, sometimes moving eastward against the stars, sometimes appearing to pause, sometimes even moving westward in what we call retrograde motion. Yet all their wanderings were confined to the zodiac, this band of constellations that wraps around the sky. Now we must consider an even slower motion, one that operates on timescales so vast that human civilization has barely existed long enough to notice it. This is the very slow turning of the sky itself, a phenomenon called precession. Earth's axis slowly precesses over approximately 26,000 years. Precession is a wobbling motion, like a spinning top that's beginning to slow down. Earth's axis doesn't point in a fixed direction forever. Instead, it traces out a slow circle in space, taking roughly 26,000 years to complete one full wobble. The tilt of the axis remains about the same, 23.5 degrees, but the direction in which the axis points gradually changes. The celestial poles trace circles among the stars as a result of this precession. Right now, Earth's north axis points almost directly at Polaris, making it our North Star. But this is a temporary arrangement. As the axis precesses, the north celestial pole will slowly move away from Polaris, circling through other regions of the northern sky over the millennia. 13,000 years from now, halfway through the precessional cycle, Earth's north axis will point toward the bright star Vega. Vega will become the North Star for civilizations in that distant era. The circumpolar constellations will be different. Stars that never set for us will rise and set for them. Stars that we can never see will become circumpolar. The entire geometry of the sky will shift, not because the stars have moved significantly, but because our axis points in a different direction. Polaris is only temporarily the North Star, and it hasn't always been so. 5,000 years ago, when the pyramids were being built in Egypt, the north celestial pole was closer to a star called Thuban in the constellation Draco. The ancient Egyptians would have used Thuban as their pole star, if they used one at all. Go back further, and there was no bright star near the pole. Travel forward into the future, and there will again be times when no bright star marks the celestial pole, making navigation more difficult for those eras. This precession affects more than just which star happens to be near the pole. Star coordinates slowly drift as the sky's grid shifts. Astronomers measure positions in the sky using a coordinate system based on the celestial poles and the celestial equator. But if the poles are moving, then the entire coordinate grid is slowly rotating. A star that has coordinates of a certain right ascension and declination today will have slightly different coordinates a century from now, not because the star moved significantly, but because the grid itself has shifted. This means astronomical catalogs must specify an epoch, a particular date for which the coordinates are valid. You might see coordinates listed as J2000, meaning they're accurate for the year 2000. To use those coordinates accurately decades later, astronomers must apply corrections for precession. The effect is small year to year, but it accumulates. Over centuries and millennia, it becomes substantial. Precession also shifts the dates of the equinoxes and solstices relative to the stars. The vernal equinox, the point where the sun crosses the celestial equator going northward, slowly moves westward through the zodiac. Right now, the vernal equinox is in Pisces, though astrologically it's still associated with Aries due to traditions established 2,000 years ago. In a few centuries, the equinox will move into Aquarius, the so-called Age of Aquarius. This slow drift of the equinoxes through the constellations is called the precession of the equinoxes, and it was discovered by the Greek astronomer Hipparchus over 2,000 years ago. Even with all this talk of fixed stars and rigid patterns, we must acknowledge a deeper truth. Stars are not truly fixed, not in any absolute sense. They merely appear fixed over human timescales because they're so incredibly distant, and their true motions are so slow relative to those distances. Stars orbit the Milky Way, our galaxy. The sun, along with all the stars we can see with our naked eyes, orbits the center of the Milky Way in a vast, stately galactic dance. The sun takes about 225 million years to complete one orbit around the galactic center. In all of human history, in all the time since our species evolved, the sun has moved only about 1/8 of the way around the galaxy. The stars around us are fellow travelers in this galactic orbit, but they're on slightly different paths at slightly different speeds. Each star has its own velocity through space. Some stars are moving toward us, some away. Some are overtaking us in the galactic orbit, some falling behind. Some are moving perpendicular to the galactic plane, bobbing up and down like horses on a carousel. These velocities, measured in kilometers per second, are substantial. The sun itself is traveling at about 220 kilometers per second in its orbit. Other stars have their own significant speeds. Yet despite these impressive velocities, proper motion is usually tiny and slow. Proper motion is the term astronomers use for the apparent motion of a star across the sky, perpendicular to our line of sight. It's measured in tiny angular units called arcseconds per year. Even the fastest moving stars visible to the naked eye have proper motions of only a few arcseconds per year. There are 3,600 arcseconds in 1 degree, so these stars are moving a tiny fraction of a degree per year. Barnard's star, which has the largest proper motion of any star, moves about 10 arcseconds per year. At that rate, it would take about 180 years to move a distance equal to the diameter of the full moon. Most stars move far more slowly. Typical proper motions are measured in hundredths or thousandths of an arcsecond per year. At these rates, thousands or tens of thousands of years pass before the motion becomes noticeable to the naked eye. This is why the constellations appear fixed. The stars are moving, yes, but so slowly and from such distance that their patterns persist across human history. The Big Dipper that ancient humans saw was essentially the same Big Dipper we see today, but it was not identical. Careful measurements show that the handle has straightened slightly, that angles have shifted by small amounts. Give it another 50,000 years, and the Big Dipper will be noticeably distorted, its shape changed by the accumulated proper motions of its component stars. Some stars are moving faster than others. The stars nearest to us tend to have larger, proper motions because they're close enough that their movement shows up more easily. Distant stars, thousands of light years away, appear almost perfectly stationary because their true motions are dwarfed by the vast distances involved. The stars in faraway clusters and in other parts of the galaxy appear completely fixed, their individual movements lost in the immensity of space. As you prepare for sleep, consider these nested layers of motion. The daily rotation that wheels the stars across the sky each night, the annual motion of Earth around the sun that shifts the constellations through the seasons, the planets wandering along the zodiac in their own orbits, the slow precession of Earth's axis tracing circles over millennia, and finally, the true motions of the stars themselves, each following its own path through the galaxy, so slowly that human civilization barely glimpses their journey. We live in a dynamic universe, but one where the motions operate on such different timescales that we can perceive some easily and must deduce others through careful measurement and patient observation. The stars move across our sky through geometry and perspective. The stars drift through the coordinate grid through precession, and the stars journey through space through their own galactic orbits. All of this motion layered together creates the sky we see, a sky that appears eternal and unchanging, yet is actually fluid and dynamic, revealing its secrets only to those who watch carefully and think deeply about the turning of the cosmos. Among all the stars in the night sky, some reveal their motion more readily than others. Nearby stars move the most across our view, and Barnard's star is a famous example of this phenomenon. Located only about 6 light-years from Earth, Barnard's star is one of our closest stellar neighbors. Despite being too faint to see with the naked eye, requiring a telescope to spot, Barnard's star has the distinction of having the largest proper motion of any known star. This small red dwarf races across the sky at about 10 arc-seconds per year. To put that in perspective, it moves the width of the full moon every 180 years or so. That might not sound fast, but in astronomical terms, it's remarkable. Barnard's star is sprinting through space at about 140 kilometers per second relative to the sun, and because it's relatively close to us, we can actually watch it move against the background of more distant stars. Astronomers have tracked Barnard's star for over a century, carefully measuring its position year after year, watching it creep northward through the constellation Ophiuchus. This star is actually approaching us, moving closer to the sun, and in about 10,000 years, it will be at its nearest point to our solar system, about 3 3/4 light-years away. Then it will begin receding, continuing its journey through the galaxy. Other nearby stars also show measurable proper motion. Alpha Centauri, our very nearest stellar neighbor at just over 4 light-years away, moves about 3.5 arc-seconds per year. Sirius, the brightest star in our night sky and only about 8.5 light-years distant, shifts about 1 1/3 arc-seconds annually. 61 Cygni, Epsilon Indi, Tau Ceti, all these nearby stars are slowly changing their positions relative to the more distant stellar background. These movements are real and measurable, but they require precise instruments and patient observation to detect. To the naked eye, even over a human lifetime, these stars appear to hold their positions perfectly. Their motion is too slow and subtle for our eyes to register without the aid of careful measurement. Yet time is patient, and over tens of thousands of years, constellations will change shape. The patterns we know today are not eternal. They are snapshots, frozen moments in a much longer story of stellar motion. The Big Dipper, that familiar pattern in Ursa Major, has looked roughly the same throughout human history, but it has not always had its current shape, and it will not keep this shape forever. 100,000 years ago, the Big Dipper looked noticeably different. The handle was more curved, the bowl slightly distorted. The stars we see as the pattern were in different relative positions because they're each moving on their own paths through space, and they're at different distances from us. 100,000 years from now, the Big Dipper will again look different, perhaps unrecognizable. The two outer stars of the bowl are moving in opposite directions from the other 5 stars, and over time, this will stretch and distort the familiar asterism. Orion too will change. Betelgeuse and Rigel and the belt stars are all moving independently. Given enough time, the hunter's shape will morph into something new, something no human culture has ever named. The patterns our ancestors gave names to, the shapes that guided sailors and marked the seasons, are temporary arrangements of stars that happen to align from our perspective during this particular epoch of galactic history. This eventual transformation of the constellations reminds us that even what seems permanent and eternal is actually fluid when viewed on cosmic timescales. The sky we know is our sky, the sky of this era, but it's not the sky of the deep past or the distant future. There are even more subtle motions we cannot see with our eyes alone, motions that reveal themselves only through precise measurement and careful analysis. One such motion is parallax, which makes nearby stars wobble slightly each year as Earth orbits the Sun. Parallax is the apparent shift in position of a nearby object when viewed from different locations. Hold your finger out at arm's length and look at it with one eye, then the other. Your finger appears to jump against the distant background. That's parallax. As Earth orbits the Sun, we view the nearby stars from slightly different positions 6 months apart, and those stars appear to shift very slightly against the background of much more distant stars. This parallax wobble is incredibly small. The effect is less than 1 arcsecond for even the closest stars. Proxima Centauri, the nearest star to our Sun, has a parallax of only about 3/4 of an arcsecond. That means, as Earth travels its entire orbit, this nearest star appears to shift back and forth by less than 1 arcsecond against the distant background stars. 1 arcsecond is the angle subtended by a coin viewed from about 4 kilometers away. It's extraordinarily tiny. For stars farther away than about 100 light-years, the parallax becomes so small that it's difficult to measure even with sophisticated instruments. For stars thousands of light-years away, parallax is essentially unmeasurable from Earth's surface, though space telescopes have extended our reach. This parallax wobble happens every year, a tiny oscillation that betrays the star's distance and our own orbital motion, but it's completely invisible to the naked eye. Another hidden motion is radial motion, the component of a star's velocity directly toward or away from us. Radial motion is detected by Doppler shifts, not position changes. When a star moves toward us, the light waves it emits get compressed slightly, shifting the spectrum toward the blue end. When a star moves away, the waves stretch, shifting toward the red. These Doppler shifts in the star's spectral lines allow astronomers to measure how fast the star is approaching or receding. Radial velocities can be quite substantial. Some stars are approaching us at dozens of kilometers per second, others receding at similar speeds. But this motion toward or away doesn't change the star's position in the sky. A star could be rushing toward us at 100 kilometers per second, and we'd never notice by looking at its position. Only the spectrum reveals this hidden dimension of motion. These motions, proper motion across the sky, parallax wobble, and radial velocity matter scientifically, not visually. They're crucial for understanding the three-dimensional structure of our stellar neighborhood, for calculating distances, for mapping the motion of stars through the galaxy, for discovering binary star systems and even planets through their gravitational effects. But they don't change our experience of the night sky. They don't alter what we see when we look up on a clear night. The sky we observe is governed by the larger, more obvious motions: the rotation of Earth, the orbit of Earth around the Sun, the precession of our axis. These are the motions that create the patterns we experience: the rising and setting, the seasonal shifts, the circumpolar circles. The subtle stellar motions are there, happening constantly, but they operate beneath the threshold of visual perception, revealed only through the precise instruments of modern astronomy. And now, after this journey through the mechanics and mathematics of celestial motion, let us return to the experience itself, to what it feels like to stand beneath the night sky and watch the stars move. What looks like motion is mostly Earth moving. When you see the stars glide from east to west, you're not watching the universe rotate around you. You're feeling indirectly the rotation of the ground beneath your feet. The planet turns, and the stars reveal that turning. You are a passenger on a spinning world, and the stars are the distant, steady landmarks that show you your own motion. This is a profound realization, one that took humanity thousands of years to fully accept. We feel stationary. The ground seems solid and still. But the stars tell a different story. They write our motion across the sky in graceful arcs and circles, patient witnesses to the truth of our cosmic situation. Stars glide on invisible circles around the poles, each following its predetermined path with perfect regularity. Some circles are complete, keeping stars perpetually above the horizon. Some circles are half hidden, creating the familiar rise and set we see most nights. Some circles are entirely below our horizon, keeping vast portions of the sky forever hidden from our particular vantage point. But all are circles, all are smooth, all are predictable. Constellations are ancient patterns riding those paths, holding their shapes as they journey across the darkness. Orion rises in the east with all his stars in place, climbs across the southern sky, and sets in the west with his pattern intact. The summer triangle of Vega, Deneb, and Altair wheels overhead, maintaining its shape through the night. Cassiopeia circles the North Pole, her distinctive W shape rotating, but never distorting. These are the patterns that have accompanied human history, that appeared in countless myths and stories, that guided travelers and marked the passage of time. The sky feels steady because change happens on vast timescales. From night to night, from year to year, from lifetime to lifetime, the sky appears essentially unchanged. The same constellations appear in the same seasons. The same stars mark the same positions. This steadiness provided our ancestors with a sense of cosmic order, a reliable framework in an often chaotic and unpredictable world. But underneath this apparent constancy, motion is everywhere. Earth spins, creating the nightly dance of rising and setting. Earth orbits, shifting the seasonal patterns and hiding different constellations behind the sun at different times of year. Earth's axis precesses, slowly changing which stars are circumpolar and which star marks the pole. And the stars themselves drift through space on their galactic orbits, gradually reshaping the familiar patterns over timescales longer than human civilization has existed. All of these motions are real, but they operate on different scales. Some we experience directly every night, some we notice over months and years, Some require careful measurement to detect, and some will only become apparent thousands of years from now, long after we're gone. As you settle into sleep tonight, you can carry with you this understanding of the moving sky. The stars are not painted on a dome. They're distant suns scattered through three-dimensional space, each with its own motion, its own story. Yet from our perspective, riding on our spinning, orbiting planet, they appear to move in unison, creating the grand procession from east to west, the seasonal shifts, the eternal circles around the poles. This is the gift of perspective, the way our particular viewpoint creates pattern and meaning from the chaos of cosmic motion. We see order because we're part of the dance. We see circles because we're turning. We see rising and setting because we're on a sphere. The sky's motion is our motion, reflected back to us in the patient, steady glide of distant stars. Rest now, knowing that above you, even as you sleep, the stars continue their ancient paths. They rise in the east as they have for billions of years. They arc across the meridian, marking the passage of hours. They set in the west, completing their daily circles. And tomorrow night, they'll return, perhaps a few minutes earlier, continuing the slow seasonal drift that marks the turning year. The sky moves, the earth moves, and yet beneath all this motion is a deeper stability, the unchanging laws that govern the cosmos, the geometry that makes it all predictable, beautiful, and true. After all we've explored together, after tracing the circles and arcs, the seasons and the drifts, the visible motions and the hidden ones, we arrive at a simple but profound truth. Watching stars is watching Earth move through space. When you stand beneath the night sky and observe the stars gliding overhead, you're not simply a passive observer of some distant celestial machinery. You are an active participant in cosmic motion. The stars themselves are relatively still from our perspective, fixed in their patterns, anchored in space. What moves is you. What turns is the ground beneath your feet. What orbits is the planet you call home. Every star that rises in the east is announcing Earth's rotation. Every constellation that sets in the west is marking the completion of another fraction of our planet's daily spin. The smooth, predictable sweep of the heavens from horizon to horizon is nothing more and nothing less than the record of our own movement, written in light against the darkness. When you notice Orion appearing earlier each evening as autumn turns to winter, you're witnessing Earth's orbital journey around the sun. When the summer constellations give way to those of fall, when Scorpius replaces Leo in the midnight sky, you're watching the evidence of our planet's 365-day voyage through space. We travel millions of kilometers each day in our orbit, and the stars mark that journey for us, shifting their positions clock hour by clock hour, revealing where we are in our annual circuit. The stars are our reference frame, the stable markers against which we can measure our own motion. Without them, we might never know we were moving at all. The ground feels solid. The air feels still. We have no sensation of spinning at over 1,000 kilometers per hour at the equator. No feeling of hurtling through space at 30 kilometers per second as we orbit the sun. Our senses tell us we're stationary. But the stars know better. The stars reveal the truth. They rise and set, not because they're moving, but because we are. They shift through the seasons, not because they're wandering, but because we're traveling. They trace circles around the poles, not because the sky is rotating, but because Earth is turning beneath them. This realization connects us to the cosmos in an intimate way. We are not separate from the universe, not isolated observers watching from some fixed platform. We are embedded in the motion of the solar system, carried along on a spinning, orbiting world that is itself moving through the galaxy. When we watch the stars, we're watching our own journey made visible. There's something deeply peaceful about this understanding. The apparent motion of the stars is not chaos or randomness. It's geometry and consequence, the natural result of our place in space and our movement through it. Every night, the pattern repeats with perfect regularity because the motion that creates it is regular. Earth spins at a constant rate. Earth orbits in a predictable ellipse. The laws of physics that govern these motions are stable, unchanging, reliable. This reliability means that the sky is, in a sense, a clock and a compass and a calendar all woven together. The position of the stars tells you the time of night. The seasonal constellations tell you the time of year. The height of the celestial pole tells you your latitude on Earth. All of this information is encoded in the apparent motion of the stars, and all of it ultimately reflects Earth's motion through space. Our ancestors understood this connection instinctively, even if they explained it differently. They watched the stars to know when to plant crops, when to harvest, when to prepare for winter. They used the stars to navigate across trackless oceans and featureless deserts. They marked the hours of the night by the positions of familiar constellations. The stars were their connection to cosmic order, their proof that beneath the apparent chaos of daily life, there were patterns, rhythms, and cycles that could be trusted. We still carry that ancient relationship with the stars, even in our modern world of electric lights and GPS satellites. When we look up and see the familiar constellations wheeling overhead, we're tapping into something primal and profound. We're acknowledging our place in the universe, our motion through space, our connection to cycles larger than ourselves. Watching stars is meditation on motion. It's a way of feeling indirectly the movement we can never sense directly. It's a way of understanding that we live on a dynamic planet in a dynamic solar system, in a dynamic galaxy, and that all of this motion creates the beautiful patterns we see painted across the night. As you drift into sleep now, perhaps you can imagine yourself on this turning Earth. Feel the planet rotating slowly beneath you, carrying you eastward through space while the stars appear to glide westward overhead. Picture Earth in its orbit, sweeping around the sun, changing your perspective on the distant stars week by week, month by month. Visualize the geometry of it all, the circles, the spheres, the tilted axes, the vast distances, all combining to create the gentle, predictable motion of the night sky. You are not still. You have never been still. You are a traveler through space, riding on a planet that spins and orbits and drifts through the galaxy. The stars are your companions on this journey, the distant markers that reveal where you are and how you're moving. They rise and set in their appointed times, not because they must, but because you do. Because Earth turns, because Earth orbits, because you are always in motion, even when you feel perfectly at rest. This is the final gift of the stars. They show us our own motion made visible. They transform the abstract knowledge that Earth moves into a direct, visual experience we can witness any clear night. They connect us to the cosmos, not as outsiders looking in, but as participants in the grand dance of celestial mechanics. So rest now, traveler. Rest on your spinning world beneath the wheeling stars. Let the ancient patterns comfort you with their regularity. Let the knowledge of cosmic motion inspire you with wonder. The stars will continue their apparent journey across the darkness, marking time, marking space, marking the eternal motion of Earth through the infinite night. And when you wake, they will have completed their circles and begun again, patient and eternal, waiting for you to look up once more and remember, watching stars is watching Earth move through space. It always has been. It always will be. And in that simple truth lies all the beauty and mystery of our relationship with the cosmos. Sleep well beneath the turning sky.